We have a 5 kilogram object moving at 7 meters per second, approaching an 8 kilogram object moving in the opposite direction at 3 meters per second. We implicitly choose this rightward direction as the positive direction. Now we could have chosen the other direction, but we choose this one. So that the velocity of the first object is 7 meters per second, positive 7 meters per second. The velocity of the second, negative 3 meters per second. Okay, B stands for before, A stands for after. So this is the state of the system, the two object system, before collision. After collision, the first object has velocity u1, 4 meters per second. I'm using u1 for the velocity after collision, v1 for the velocity before the collision. And for the second object, v2 and u2 are similarly defined. So that u1 is 4 meters per second. That's given that after the collision, the 5 kilogram object is moving at 4 meters per second. And we want to find u2, the unknown velocity of the second object after collision. Now, in a two-object collision, an isolated collision with no other external forces acting on the two objects, only force, the net force being the interaction force between the two objects. The two objects exert equal and opposite forces on one another for the same time interval. It follows then that the change in momentum of the first object equals the change in momentum of the second. So that, change in momentum of the first object is going to be the momentum after collision minus the momentum before collision. Now, before collision, the momentum is the product of 5 kilograms with the 7 meter per second squared velocity. After collision, it's the 5 kilogram mass multiplied by the 4 meter per second velocity. So here we have the change in momentum of the first object. Change in momentum of the second object is the momentum after the 8 kilograms times the unknown after collision velocity u2 of that object, minus the 8 kilogram times negative 3 meter per second momentum of the second object before collision. Well, this is an easy equation to solve for u2. We simply first distribute the negative sign through here, and there really is a plus sign there, but in moving the board we kind of lost that. No, I'm sorry, that is a minus sign. Never mind. It really did look like there was a plus sign that had been kind of obliterated there. But we have minus, minus, and minus, so that certainly is minus. Yeah, this one, of course, is minus. Okay, so we add 15 kilogram meters per second to both sides. We get negative 9 kilogram meters per second on this side. We add the 8 kilograms times u2 over here. We get this. And this is all very straightforward. Then we divide by the 8 kilograms. We find that u2 is 1 1/8 or 1.125 meters per second. Now, I'm not sure where the significant figures lie in this, but if these are exact figures, then that would be an appropriate response. And it's a negative 1 1/8 meter per second. Okay, so that was very straightforward. The kinetic energy after collision is clearly less than the kinetic energy before. Why is that? Well, the speed of the first object after collision is less than it was before, and so is the speed of the second object. So that when we calculate the kinetic energies after, it's clearly going to be less than the kinetic energy before. Both speeds decrease. Okay, then we have a side comment here. For the 5 kilogram object, the change in velocity is what? It's negative 3 meters per second from 7 to 4. The second object, the change in velocity is plus 1.875, 1 7/8 meters per second, because the speed actually went from negative 3 meters per second to negative 1 1/8 meter per second. That's an increase or a positive change in the velocity. Okay, it lost speed, but the velocity showed an increase. Then the thing we want to show is that the I'm going to put the subscripts in these. Delta V1 is negative 3 meters per second. Delta V2 is 1.875 meters per second. And I'm going to say that the change in velocity of the second object divided by the change in velocity of the first object is equal to the mass of the first object divided by the mass of the second object. And you can easily check that out. I have to say that's equal to the negative ratio. Okay. But if you rearrange this, you get M2 delta V2 equals negative M1 delta V1, which means that the changes in momentum are equal and opposite. But the way this feels, you have the greater mass here, and it's going to have the lesser change in its speed. And you have the lesser mass here, it'll have the greater change in speed, and those changes are going to be in inverse proportion to their masses. Also, the velocities will have equal and opposite. Will have changes of opposite. I said equal and opposite. Will have changes of opposite sign. If one velocity increases, the other will decrease. So this one increase, this one decrease. And this is important intuitively. The ratio of the masses is mass 1 to mass 2 is 5/8. So the ratio of the velocity changes will be 5/8. This will be 5/8 of this, except the negative.